Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to go over precipitation reactions and net ionic equations. So let's get into this. So the first thing we need to talk about is precipitation reactions. What is precipitation? Well, let's talk about precipitation reactions. Precipitation reactions are a subset or a kind of double displacement reaction in which one of the products is insoluble in water. What does that mean, insoluble in water? Well, that means that it cannot be dissolved in water. So when the product forms, it can't stay in solution. It's going to come out of solution. It's going to form a solid, and this usually results in cloudiness in your solution. So you start off with two clear solutions, you mix them together, all of a sudden you see cloudiness. That indicates you have a solid forming, and if you give it some time, it may, usually, likely, is going to settle to the bottom and you'll see the solid form that way. So usually it's very clear cloudiness that forms that indicates that you have an insoluble substance that was formed, meaning it can't be dissolved in water. And so let's talk a little bit more about double displacement reactions. So a double displacement reaction, as the name implies or indicates, is that you have a displacement of two things, double. So two things are being switched with each other. So in this case here, I have this generic equation. You've probably maybe seen this before, I don't know. But here I have substance with A and B atoms together. And here I have a substance with a C and D atoms together. And what happens is that they change partners. The analogy I like to use is ballroom dancing, right? So maybe two people are doing the tango, or whatever ballroom dance you can come up with. And so you have two couples, man and woman, dancing together, another man and woman dancing together, and they're dancing, and then all of a sudden they decide, hey, would you like to switch partners? And so they switch partners. So the woman that was with one man goes with the other man, and the man that was with that woman goes with the other woman, and they start dancing and they switch partners, right? So that is a double displacement reaction. This is also referred to as a double replacement reaction or a double exchange, or other terms are used as well. So don't confuse double displacement as if it's something different from double replacement or double exchange. They're all the same thing. Okay, so here, to follow the ballroom analogy, right? So I have my two partners here. So here's, positive ion is always written first. So we'll call the positive ion the man, and the negative ion is going to be the woman. So you have, positive, negative, positive, negative. Remember, the positive, negative can only go together. You can't put a positive with a positive or negative with a negative, right? So in the same way, to follow the ballroom analogy, traditionally it's basically man and woman dancing together, not man and man, not woman and woman, right? So you can see the A is going to go with the D here. So positive is going to go with the negative on this side. So the two outer ions come together to form a product, and the two inner ions come together to form the product. And notice that C here is positive, and so positive is always written first. So positive C, and then the negative anion B. So always remember, when you're doing a double displacement reaction, you put the outside ions together to form a product. You put the inside ions together to form the product. When you form the product and you put those ions together, please make sure that you balance the charge and figure out what the subscripts are, what the new subscripts are going to be. Don't just assume that if you have a 2 subscript for A over here, oh, it's got to be a 2 subscript there. That doesn't always work, and it doesn't work like that. So if you're putting 2 new ions together, remember, your ionic compound has to be balanced in charge. So you got to figure out what subscripts you need in order to get zero charge overall for your ionic compound. Okay, so now once you've figured out what the subjects are, what the products are, you have to figure out whether a precipitate forms. Does a precipitate form? Does a solid form? Is it insoluble in water? Are any of these insoluble in water? And to do that, you got to use your solubility rules. I'll cover that in another video. But for now, we'll assume that one of these is insoluble in water, and so therefore it becomes a precipitate. So the precipitate is what we refer to as the solid that forms from the reaction of your two reactants. So if one of these is a solid or insoluble in water, that is the precipitate. Okay, so let's actually go over a real example. So here I have calcium nitrate, CaNO32, aqueous. So aqueous in your equation means it's dissolved in water. So this is soluble in water because aqueous tells me it is. So anytime you have an aqueous, that means it's dissolved in water. These are actually separate in water. So aqueous. Here I have sodium carbonate. That is aqueous too. So these are soluble in water. And what I have here is a kind of a picture to help you visualize what these actually look like in water. When we write it like this, it seems that we're putting them together in a formula. And so this formula makes it seem like these are together in solution, but in reality, these are separated from each other. So remember, the water is surrounding the ions, separating them, keeping them separate. So here is what it actually looks like in water. So if this is a beaker of my calcium nitrate, if I have, I made the blue dots would represent the calcium, the orange dots would represent the nitrates. So if I have this in water and it's aqueous, then these ions are actually separated from each other in the water solution, right? So they're not stuck together. We write it that way because that's the formula, but we have to realize in actuality, these are separated, floating around in solution, not really interacting with each other. Same thing with the sodium carbonate. So I made the sodium red and the carbonate green. Even though we're writing these together in a formula, since it's aqueous, in reality, they're separated from each other. They're not really together in solution. They're separated. So here's what the beaker would look like in reality. So the sodium and the carbonate ions are separated from each other. So the reds and the greens are not really interacting with each other. They're separated. They're floating around in solution, minding their own business, right? So both of these are aqueous solutions. Now, what happens when we mix these together? So once I mix these together, I'm going to get possibly a reaction. And it'll depend on the solubility of the ions together. Now, notice these are two solutions that are separate. These ions are not in contact with these ions. So they are separated from each other. But when I mix them together, now these ions can interact with each other. Before they're separate, when I mix them together, now they can interact. And notice here that the calcium and the carbonate ions come together to form a solid. So the carbonate and the calcium are separated in different beakers, right? So they're not interacting with each other, but when I mix them together, now they can come together. So the outside ions can actually interact with each other to form a possible product, calcium carbonate. And it turns out that calcium carbonate is insoluble in water, so it forms a solid. So S for solid. So the blue and the green come together. And so you can see that in the picture I have, that the green and the blue have come together to form a solid, and it's down on the bottom where solids would form, where they're going to end up. And so you can notice that the green and the blue, the calcium and the carbonate are now bonded together. They're closely associated with each other, and they're forming these units. What about the sodium and the nitrate? The sodium and nitrate is aqueous, meaning that those ions are still floating around in solution doing nothing. They're not really interacting with each other. Now, again, we write it together as a possible product, but these really are not together in solution, and you can see that here in the picture. So the red and the orange, so these are red, 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 red. I know it might be hard to tell in the video, but this is orange, 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 and they're not really interacting with each other. They're floating around in solution. So what I have over here is orange and red ions floating around in solution, really not doing anything. Then I mix them together. The red and the orange ions are still floating around doing nothing. Nothing's changed with respect to the orange and the red. The nitrate and the sodium are still floating around. So they were floating around before they got mixed together, and they're floating around minding their own business after they got mixed together. So they're really not doing anything. They're not really participating in any reaction. And this is what we refer to as spectator ions, right? Think of the analogy with a sporting event. You go to the football game, or for me, I love wrestling. I was a wrestler throughout high school, middle school, elementary school, a little bit in college, not so much in college. I miss it though. But you're going to a spectator sport, right? So you're going to a wrestling match or a wrestling meet or a tournament or a football game or hockey or whatever the sport you want to think of. So you're there, you're in the stands, you're a spectator. Are you participating in the sport? Am I down there wrestling? No, I'm watching, I'm spectating, I'm not really doing anything. I'm not part of the action, right? I'm not part of the sport or the tournament or the meet or whatever, right? So I'm just spectating. The players out there are the ones doing the action, right? So the same thing with the ions here. So the ions that are not doing anything, they're not participating in any sort of reaction, they're not doing much, right? They're just floating around in solution. Those are spectator ions. They're not in part of the reaction. And so when we will get rid of those when we write what is called a net ionic reaction. And I'll get to that later in this video. But that's what I want to point out. So these guys here, the red and the orange, the nitrate and the sodium are not doing anything. They stay aqueous. They're aqueous here, they're aqueous here, and they're aqueous here, meaning that they are dissolved in water and they stay dissolved in water. These guys here, the calcium and the carbonate, those are coming together. They're actually participating in a reaction. So they're the players involved in this activity, in the reaction, not the sodium and the nitrate. Okay, so that's really important to keep in mind when we talk about the molecular equation, complete ionic equation, and net ionic equations that I'm going to talk about in just a moment. But I want to point out this equation here, this is called a molecular equation. Why? Because even though these are ions that are separated in solution, like the picture shows, these are separated in solution, these are separated in solution, we write them together as if they're together in a molecular form. So we call this a molecular equation. Yes, it's kind of a misnomer in the sense that these are not molecules, but the idea is that we're kind of putting them together and they're treated as one unit, even though really they're separated in solution. So this is called a molecular equation. And then what I'm going to show you is the difference between the molecular equation, the complete ionic equation, and the net ionic equation. So stay tuned. Okay, welcome back. So let's talk about molecular equations, complete ionic equations, and net ionic equations. So here I have the equation I had before. So like I said, this is a molecular equation because it's putting all the ions together, even though they're really not together. They're putting them together as compounds, as if these two are stuck together. So calcium nitrate is written together as in a formula. So it can think of this as a molecular formula or a chemical formula. So when your substances are written together such that the ions are together in the formulas, we call this a molecular equation or a balanced molecular equation because it's balanced, right? So all chemical equations should be balanced. So here we have a balanced molecular equation. Here I'll put balanced in here. So balanced. So a balanced molecular equation. So then how do you get the complete ionic equation? Well, the complete ionic equation, as the name implies, is that everything is written completely ionic, right, into ions. So for any ions that are aqueous, we're going to separate those out, and this is going to be more true to reality. So just like I was talking about before with my pictures, that the ions that are aqueous really are separated from each other. So in the complete ionic equation, we separate any ions that are aqueous. So here we have calcium and nitrate. So we're going to separate those. We have calcium 2 plus aqueous. And so it's important to remember that when you write the ions separately, you write the charge. So calcium has a 2 plus charge. So we're separating the calcium from the nitrates. So here we have one calcium atom with a plus charge, aqueous, plus. And notice here also, this subscript tells us we have two nitrates that are needed to balance the charge on the calcium. So since we have two nitrates there, we're going to have two nitrates here, but we don't write it as a subscript. We only write it as a subscript to identify that these are part of the formula, right? But when we're trying to indicate that these are separate entities floating around in solution, we put a 2 coefficient. So the 2 subscript becomes a 2 coefficient. So we have two nitrates, NO3 minus aqueous. So we just took the two ions here and separated them. So calcium is separated from nitrates, and they're floating around in solution, right? Just like they are in reality, they're separated from each other. So we do the same thing with the sodium and the carbonate. So here we have two subscripts, meaning we have two sodiums. So here we're going to have two Na pluses. So two Na pluses. So the subscript becomes the coefficient. Two sodium ions, aqueous, and then we have the one carbonate plus CO3, 2 minus, aqueous. So we've separated all of the ions. Just like in the picture of the beakers, everything, all the ions were separated from each other. They're really not together. So we're kind of showing that in our complete ionic equation. So this is the reactant side. What about the product side? So you'll see here that this is a solid. So the calcium and the carbonate really is together in solution, just like we saw in the picture. So we're going to keep that together. Anytime you have a solid or a liquid that's produced, or in a reactants, if you have a solid or liquid here, or if you have a solid or liquid here, we don't separate those in the complete ionic equation. They're actually together. So here, this is a solid. These stay together, so we keep them together here. So the calcium carbonate stays a solid here, and that matches really well with the picture that I drew. And then here, because this is aqueous, the sodium and the nitrates are separated from each other. So here we have a 2 coefficient. That applies to everything in the formula. So we have two sodiums and we have two nitrates. So that's what we have here. So 2 sodium plus aqueous plus 2 NO3 minus aqueous. And so that, ladies and gentlemen, is your complete ionic reaction. Every ion is separated except for those that are in solids and liquids. So this is a solid, so it stays together. Okay, now I talked earlier about spectator ions. Remember, spectator ions are the ions that aren't involved in the reaction. They're just doing nothing. They were floating around in separate beakers before they were mixed together. And then once they're mixed together, they're still floating around doing nothing. They're really not interacting with anything. So you can identify the spectator ions by the ions that don't change from the left and the right. they stay pretty much the same, right? So here I have 2NO3 minus aqueous. I have two nitrate ions that are in the aqueous phase on this side, and I have two nitrate ions in the aqueous phase on this side. So they really haven't changed. They're still aqueous. They're still dissolved in water. They're still floating around doing nothing. Same thing with the sodium ions. I have two Na plus aqueous here, and I have two Na plus aqueous here. So again, just floating around in nothing. I'm sorry, still floating around in water doing nothing. So they're not floating around in nothing. Sorry, that was a mistake. So because these ions really are not doing anything, they're called spectator ions. And so we remove them from the equation when we do our net ionic equation. So think about net ionic equation. What does net mean? For those of you who have a job and you have a paycheck, and there's this difference between what is called the gross pay and your net pay. Your gross pay is before taxes. It's your overall amount that you would get paid if the government didn't take money or taxes out of your paycheck. The net pay is what you get after the government has taken taxes out of your paycheck. Whatever's left is the net pay. So that's what you actually get to put in your bank account. So for the net ionic equation, you're going to write with the spectator ions removed from the equation. So whatever's left is your net ionic equation. So you have calcium 2 plus, that stays. These are removed. The carbonate ion stays. And then the solid that was formed stays. And so this is what's happening in the reaction. These are the players. You remove the spectators, and what's left are those who are involved in the activity, in the reaction. So we have calcium plus 2 plus the CO3 2 minus, your carbonate, gives you calcium carbonate solid. That is insoluble in water. And so again, the balanced molecular equation is everything written together in formulas. Aqueous, solid, aqueous, aqueous. The complete ionic equation is anything that is aqueous. All the ions that are aqueous are separated into their separate ions. Liquids and solids stay together. And then your net ionic equation is where everything stays except for the spectator ions. So spectator ions that aren't doing anything, they stay aqueous on both sides. They're going to be removed. So you get they're not really part of the reaction. So you remove them, and what's left is the reaction. So I hope that's helpful. If that was helpful, if you enjoyed this video, if you learned anything from this video, then please, by all means, like the video, share the video with your friends and family during this holiday season, right? Make sure that you click that like button somewhere over here possibly, or if it's not over here, look for it, find it, click it. Also, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic for me to cover, if you want me to cover something, let me know. Also, if you have a particular problem or a question you need answered, put it down below. I would love to do that for you. Thanks for joining me, and have a great day.